I don't know what it is about me, I just can't leave well enough alone. We have been busy along this journey designing and building a digitally controlled, fully dimmable LED illumination system. And that includes the controller, the drivers, and the luminaires themselves. All designed and built from scratch. And it works. It's wonderful. If you've been following along on the journey, hopefully you think so too. If you haven't been following along the journey, I'll make sure to put a link in the description so you can catch up. But man, even though it works, I am still dissatisfied. Let me be specific. I'm not dissatisfied with the results. The lighting system is pretty good right now. What I'm dissatisfied with is the time and effort it takes to build this thing. See, when we designed this thing, we had to make some decisions about how to organize parts on that printed circuit board. Decisions on how we would connect external devices to that circuit board. Decisions on what the enclosure, the 3D printed enclosure would look like and how things would fit inside that enclosure and how wires would connect to that printed circuit board through that enclosure. All of these decisions had to be made at the time, and I'm not happy with them. Those decisions that we made led to my frustrations that I'm going to explain to you in a little bit. But before we jump into that, I came to the decision that rather than, putting Band-Aid solutions, I'm just going to redesign it. In one of my earlier episodes, I did say I like doing things the hard way. Or actually, I think I would rather position it as I like the more scenic journey. So as we redesign this circuit, I'm going to take advantage of the opportunity and try out a different circuit design software so we can compare the old one and the new one. Now, before you start getting concerned about the sponsor of this video, let me be clear that the sponsor of this video is neither one of these PCB design software. So I'm going to give you my honest, unbiased opinion as to how these two softwares compete with one another. The sponsor of today's video is more on the manufacturing side of these PCBs. So more on that in a little bit. But first, let's get into the details as to why I was so frustrated. Honestly, I'm so proud of this. This is the 3D printed enclosure of the controller that contains a circuit board for our LED illumination circuit. It's not powered up right now, which is why there's no wires going in and you can't see any activities on the indicator, but this dial controls the intensity of the illumination once it's all plugged in. Let's open it up and take a look inside. Look at that beautiful red circuit board. Let me turn this over so you can see the other side. Look at all those nice components. This was hand soldered by yours truly. It's functional and I think kind of pretty. So these are the connectors for the drivers. Here's one of those drivers that we built and it just would snap in over here. Here's another one that I built just to test it out, make sure everything works fine. The circuitry works wonderfully and the 3D printed enclosure that goes around it is great in many ways, not so in others. Here's some of the nice things about this 3D printed case. There's a little ridge that you might be able to see right over here, and that ridge is perfectly sized for this PCB, so it fits nice and snug. Fantastic. There's two screw holes over here that allow you to anchor that PCB down, which turned out I didn't need them at all, so they're really just a waste of space. Nonetheless, the design was pretty sound. Removing these, you'll look inside and see some air holes, which are kind of neat. Look at these little slots that we designed. They're beautiful on this side and on the bottom. All of this was fantastic until we get to this part. This bit over here, this is where that PCB or the circuit communicates with the outside world. And this part led me into no shortage of frustration. The concept should have been simple enough. There's a little groove over here, which with the power lines would actually come in and connect right to these two power ports over here, and that would align really well. So that part worked out excellently. This particular controller had room for two drivers, one over here and one over here. I'm just kind of resting them in place. I'm not actually connecting them, but you can see those ports where they do connect into. And once they're connected, this port right over here, these two pins is where the power comes out for the actual LED. So the design was one wire would come out, or I guess two wires would come out, and those two wires would then be going through these two ports over here, one on one side, one on the other side. And you can see how they're kind of shaped like hexagons. Those hexagons fit these nuts perfectly. And so the idea was that I could use a screw terminal on the outside, connect to those nuts on the inside, and thus create an electrical connection. In theory, sounds wonderful. Here's what it looked like in practice. Here's another one which is partially wired up. Now I'm going to open up the side here so you could see the great difficulty in getting those wires connected. I had to make sure that every single wire was soldered in properly, the wire lead was not very long and it had to connect not only those two hex nuts, but also this short indicator, which is basically an LED. It's hard to see from that side. You can see it better over here. You see that little red LED? That thing, that's what that hole was for, to indicate that the driver is shorted out. And so there was actually 4 wires from each driver connecting to this. And look, you can already see that 2 of those have become disconnected. It just really wasn't firmly held in place. And the other thing was, when this thing is attached, the amount of space that one has to make these connections is absolutely minuscule. And with me and these gigantic sausage fingers, there is no way I was going to do this efficiently. This was one major source of frustration. Once those things were connected, the theory was I can use a single screw and a washer like this. There we go. And thread that in from the front, connect a wire to this terminal, and we'd have our connection to the driver. Here's one which had been all wired up with the terminals in place. So you can see them right over here. And just like most accidental discoveries, look what happens when someone gets a little bit too aggressive. So here's someone trying to thread this through. Put in the screw, use a screwdriver, don't twist, but push. And suddenly that nut becomes dislodged. That happened to me one too many times. And it wasn't just the controller. Take a look at the luminaire. Remember when we tested this on the last video? Yeah, the results were great, but what I didn't include in the video was the frustration I experienced putting that thing together. Here, let's take this apart so you can better see some of the issues here. The LED panel itself plugged into or was secured using these 2 holes. On the other side of this, there are some hex nuts where the LED module would connect to. That part worked really well. But if you remember, we had these little corner slots right here where the wires or leads would go into. Yes, we had 4 for symmetry. We only really needed 2. But running those wires on the other side, in theory, was a great idea. But when you flip this around, you had to run those wires down here and into 2 more hex nuts over here. Now, running the wire wasn't a big deal, but attaching them to the hex nut, oh my goodness, those soldering jobs were just so painful. There was another issue with the LED module itself. We made a video earlier about how you can use a soldering hot plate to very effectively attach these LEDs to that PCB, and it worked wonderfully. However, eventually you got to get wires connected to that same PCB, and in order to connect those wires, you have to heat up that point right over here, and heating up that point right over there meant that sometimes this LED became dislocated. Oh my gosh, and if the soldering and wiring weren't enough, here's some more problems I found out. Once the driver is securely attached to the controller, there we go, I've attached it now, so it's nice and snug. Here's one problem. You notice that there's a bit of a droop here. If you do this wrong, you might get a short one way or another. This was not very secure. The other problem I discovered is that there tends to be a little bit of torque, and if you twist this a little too much, those fragile pins down there, they break. Oh, and here's another thing. We designed these drivers with ports on the top so you can actually stack them. In theory, it worked really well, except the parts that we use to create the drivers are too big and don't let me stack. And even if they could stack, the droop would cause potential shorts when the 2 drivers touch one another. Finally, if we actually were able to stack drivers in this enclosure, you can see that the space that would be occupied would grow on this side, but over here, there's a whole lot of space that I'm not making use of. And that means the enclosure itself would have to get taller, but I'm wasting a lot of space inside. So here's some of the changes I wanted to make. Rather than using this kind of terminal, I wanted to use a screw terminal with a hex nut that would allow me to connect power directly to the board. I'd also want to extend that capability to the drivers themselves, because right now these little connectors over here are so flimsy and fidgety. With the screw terminal, I would ensure a nice solid fit. I also want to make better use of the space on this board, and rather than just having 2 drivers, I wanted to see if I could set it up so that we could put drivers all the way around and potentially even have 6 of them on one controller. Finally, I wanted to enter into a more modern era and have an option for surface mount devices. See, the through-hole design that we're using here works really well, easy to solder, but it's kind of dated. And it takes up way more space. If we used a surface mount technology, then it'll be a little bit more difficult to solder, but we'd actually have so much more space to work with, and it would look a lot nicer. So like I said before, in redesigning the circuit, we're going to use a different design software. This is the design software we've been using so far. It's DesignSpark PCB. The website is right here. Although they have an option for paid versions, I've been using the free one. So if you want to go get yourself a copy, you can do that right here. The software I chose to switch to is this one, LibrePCB, and you can get it from this website right over here. There is no paid version for LibrePCB. It is completely 100% free. Now, I said this before and I'll say it again. Neither one of these companies has sponsored this video. The sponsor for this video is PCBWay, and they're the manufacturer of my boards, which we'll get into in a minute, but I wanted to say that again because I have no biases for either of these two pieces of software. I used both of them. The design for the current board is based on LibrePCB, so we'll be able to compare DesignSpark to this one, hopefully as unbiased as possible. See, the first thing I want to touch on is this difference between free and kind of free software. See, LibrePCB, the software we're using now, is totally free. It's actually open source, so the community encourages those who have the ability to enhance the software to get in and do just that. I think it boosts the community. So there are some advantages to that, but as many of us know, when it comes to open source software, there's also some disadvantages. Now, I'm going to steer clear from that discussion of open source versus commercial. I don't want to talk about that. I want to talk about the features and capabilities of the two technologies. Nonetheless, I bring it up because when you sign into LibrePCB, it just works. When you sign into DesignSpark, it wants you to log in, and there's a whole licensing mechanism that it must call home. In fact, I was looking at the FAQ online, and it says that an internet connection is required to use DesignSpark. First, you need it to log in, and then it will check every 2 hours or so. So I've been using it for all of the designs that we've done so far. I really didn't have a problem with it. Some folks may, but I wanted to put it out there. That is one of the first differences that is of importance between the two. Once you jump into the software, there are some visual differences. This, for example, is the circuit designer for DesignSpark, and here's a circuit designer for LibrePCB. The tools and functionality available to the user are actually quite similar. But then again, that's exactly what I'd expect. Neither one of these software is professional end. They're both entry level. In the DesignSpark circuit editor, adding a component is a fairly straightforward activity. There's a little sidebar here that you can actually pin if you want it there the whole time. And just scrolling down the list, you can choose out of the devices that you want to add, and then pick the layout that you want to use. So in this case, I have the 2N3904 BJT transistor, and you can choose to use a through hole or a surface mount. Once you're happy with it, you can click and drag it to the layout and then wire it up as necessary. In LibrePCB, the process is similar. There's an Add Component button, which brings up a dialog box which you can interact with to choose any of the devices that you want and add them. And just like in DesignSpark, you can choose the surface mount or the through hole. Once you move to the PCB layout window in DesignSpark, the process for adding components is awfully similar. You have that same Add Component button or panel on the right from which you can choose your device, choose your variation, and click and drag it onto the board. One of the unique things about DesignSpark is that I could create a PCB layout and not have an associated circuit diagram or schematic that matches that PCB layout, which was really useful for me because there were times when I just really needed to quickly build a layout without creating the schematic to begin with. So in DesignSpark, those two things are or can be disconnected. Now, there is a concept of a project file in the DesignSpark, which, as far as I understand, will connect those two things together. I did not leverage that capability, so I can't comment too much. All I know is that you have the ability to keep those two things separate. Moving to the LibrePCB layout editor, there is no function to add a new component. Instead, there is a list of devices that you can place. And notice, my device list right now is completely empty, because all of the components that are on this PCB layout are there already. This is connected to the schematic you see over here. So the only way to add a new device onto this PCB layout is to add it to the schematic first. See, if I just test this out and add a new BJT transistor, I'll click OK and put it in a random place. Notice I'm getting notifications here saying that they're unconnected, but that's okay. We can proceed with this. And I switch to the PCB layout editor. Sure enough, we see that device now show up in this list. I have the ability to add this to my layout now. See, that to me was a very important distinction because I was used to DesignSpark allowing me or permitting me to create isolated PCB layouts. The first thing that I did in LibrePCB was try to create an isolated layout, and I was pulling my hair out figuratively, as to why I couldn't proceed. It took me a while to figure out that you must create a schematic first. At first, I thought that was a disadvantage, but as I started working with LibrePCB, I noticed that maintaining the integrity between the PCB layout and the circuit design was actually really good for the project. It helped me follow along with the project, especially as they got more complicated, so I knew I was doing the right things. Those differences extend into the library management components of these pieces of software. So here's the library manager for DesignSpark. We're looking at all the schematic symbols right now. And of course, as you might imagine, it comes with quite a few. You can certainly add your own libraries if you like, or perhaps even find libraries online. I didn't actually look for them. For my purposes, the schematics that it came with are good enough. If I wanted to, I can just click on the edit and make edits to those symbols as I see fit. So the library editor also lets you edit those PCB symbols. These PCB symbols are actually my library. I created this one because, well, I like to have my own footprints. And so you can see all the different ones that I've created here. Now in DesignSpark, the combination of a schematic and a PCB symbol becomes a component. So the component allows you to create multiple footprints for the same schematic, which is what we see here. We see that this NPN transistor has a TO92 through-hole footprint, as well as an SOT23 surface mount footprint. And whenever creating devices, I can use that one component and choose whichever footprint is more appropriate for my design. In LibrePCB, we also have the option of using online or other libraries that are available with it, and the list is quite extensive, as you can see here. I went ahead and created my own library. We have the concept of schematic symbols, which is similar to the schematic symbols in DesignSpark. Here's the editor, which allows me to make some edits. Not really a lot of differences here. In LibrePCB, the concept of a component is different than it is in DesignSpark. See, in DesignSpark, a component is the combination of a schematic and a PCB footprint layout. You put those together, you get a component. In LibrePCB, a component is basically a wired up schematic symbol. So if I take a look at this BJTN component, open that up, you'll see that it has the 3 required leads, the base, collector, and emitter, and the rest of this page is pretty empty. I mean, I could make some symbol variants if I wanted to, or even add some attributes. I never took advantage of those features, but right away we see that the concept of a component is a little bit different in LibrePCB. The footprint comes a little later. The footprint comes into play in this list down here. This is a list of packages that these components can exist in. Let's consider the BJT. It can exist in a TO92 package. If we open it up, here's my package with my 3 pads or pins or leads. Notice they are unnamed because a package can be applicable to different components. And that is a really unique feature that I especially like in LibrePCB. Here's the surface mount SOT23 package, which also has those 3 leads. Some of these packages may have alternate footprints, like the surface mount 16-pin IC. If I open it up, there's a default footprint that you see here. We can even get a density level A, which we can also have density level C, but all of the package pads and the pin layouts is the same regardless of the footprint variant. So you notice how this was a little different from DesignSpark. And then finally, those things are combined in what's known as devices. So here's the BJT SOT23. That's a surface mount BJT, which uses the one BJTN schematic that you see here and the SOT23 footprint. I can open up the BJT TO92, which uses the same schematic, but it uses a different footprint. So the DesignSpark method uses 3 objects, let's call it: the schematic, the PCB layout, and the component, which is a combination of those 2. In LibrePCB, it's a little bit different. We have the symbol, which turns into a component after being wired. There are a set of packages that can describe different footprints, and then the component and the package are combined in a final product called the device. And to make organizing the library easier, LibrePCB comes with this thing called component categories and package categories, which allows you to categorize these packages and devices and symbols and components into their respective categories. So right off the bat, the LibrePCB method appears to be a little bit more complex and perhaps a little bit extra as opposed to the DesignSpark. But as I started working with it, it actually makes more logical sense to me. So my preference is in the library management capabilities or the device management capabilities of LibrePCB. Now, it's not all roses and sunshine with LibrePCB. Let me show you one of my major gripes. Let's say I wanted to edit this footprint over here in DesignSpark. I can click on the edit function, And up pops your expected editor, which has all your tools up on the top and the left here. And on the right, I have this wonderful little layers tab over here, which allows me to turn layers on and off to hide them so that I can easily work in my design without interfering with other layers. LibrePCB, on the other hand, oh my gosh. Editing the SOT23 surface mount package in LibrePCB brings up this familiar editor in which I can, click on different features over here and make changes, move them around. I have my toolbar on the left and on the right, but there is no layer switcher. Even though every single one of these features has an associated layer, you can see this line right here sits on the top legend, and I can move this to guide, measures, board cutouts, etc., etc. The only one I can't move it to is pads, because pads has a very different, feature style over here. But I have layers. These things exist on their own layers. Here's top legend, just like the other one. I think this one in the middle here sits on the top documentation layer. There's even one down here which sits on the top package outline layer. But I can't turn them on and off. So as a result, editing footprints is so tedious. Now I looked and I couldn't find it, and I was shocked that I couldn't find it. So if anyone out there knows where this thing is, please let me know. Other than that, the rest of the differences are fairly minor. For example, let's turn off the bottom copper layer on this PCB layout and try adjusting some of these traces. I can click on a trace. I can get its properties, of course. This is in DesignSpark. See a little bit of information about that trace. And if I try to move it, you see how the trace moves and the mitered edges kind of collapse and expand to allow me to move this trace effectively, which is kind of nice. I can move different pieces of that trace to get a better location for what I wanted to. So I like the ability of the trace movement in DesignSpark. LibrePCB also allows me to move traces, but it's a little bit different here. Let me turn off some of the top layers so I can take a look at the bottom. There's some blue lines down here, and watch what happens when I try moving this trace up. So the trace moves, but look at those mitered edges. They don't maintain their angle. They move to match the endpoints. It also means that I can move the individual endpoints in PCB, which you can't actually do in DesignSpark. So there are some subtle differences. And notice there really isn't any functionality to look at properties for that trace. All I could really do is change its width. I can remove it, or I can do a measure, which I'll get into in a moment. In DesignSpark, I was able to do things like add a corner, edit the segment. I can even turn it into an arc. I can change its net. I can do all sorts of stuff. I can even change the layer of that particular trace. So the trace editing functionality of DesignSpark, in my opinion, comes out on top. Now about that measure tool. In DesignSpark, you can click on this little ruler icon here and then click on let's click on this pad, for example, and you can see that little line and the distance numbers here on the left are adjusting as I move around. Let's look at the neighboring pad and let's click on it. And once I've clicked on it, it's satisfied in terms of I have two different objects, and it tells me the distance between the center of those two objects. If I click here, I can actually see the gap. This is a 0.7 millimeter gap between both of those objects over here. I can even see the drill distance, so it's a 1.4 millimeter distance from the drills. So there's a lot of good information here when I use the measure tool. LibrePCB also has a measure tool, which I can click on over here. Let's click on this pad. This is actually one of the challenges. I had a hard time trying to identify or pick what I wanted to measure. So I think this is the pad there. Yeah. And then I can go up here and you can see the ruler. It actually looks kind of nicer in LibrePCB, at least I think so. And find my other pad, click on there, and it tells me that this is 2.4 millimeters away. But that's about it. It gives me my X and Y deltas. So I can see that there is no delta X, but there is a 2.4 millimeter delta Y. LibrePCB does not tell me the distance between the pads nor the drill centers. I have to figure that out on my own. But it looks a little nicer. Speaking about looks, this is totally subjective, but I think LibrePCB is way easier on the eyes. Here's all the important layers that are enabled in LibrePCB. It's a nice soft colors. Of course, I think you have the option to adjust those colors and preferences to your liking, but this looks nice. DesignSpark, not so much. I mean, I guess I could change the default colors to my liking, but I didn't change any of the colors in LibrePCB either. It's all pretty much stock. Some people may prefer the look of DesignSpark. I think I prefer LibrePCB in the looks department. Now, I mentioned earlier that both pieces of software are fairly entry level. So as you would expect, there's not a whole lot of tools to choose out of. They do what you need to do, but not much else. I mean, I was able to use the tools in LibrePCB to get everything done, and that included some custom pad layouts. It also included some copper planes that I needed to put onto the bottom of the board. So I was able to do that just fine. I really didn't need any sort of extra stuff that some of the more advanced capabilities come with. Now, having said that, I've never used any of these advanced PCB design software, so frankly, I don't know what I'm missing. DesignSpark is also quite basic, but clicking on the Tools button here, it actually hints at a whole bunch of other things here that I've never touched, but are available. Auto place components, auto fan out, I don't know what that is. Track fatten sounds kind of fun. Auto miter, whole bunch of things that I've never really used. I think the only one that I've tried using is the auto route nets. So based on a schematic design, you can have the DesignSpark automatically create the PCB layout for you based on your schematic. Maybe it was just the way I did the schematic, but my results were terrible. I did not want to use the auto design feature. I created it myself. If LibrePCB had that functionality, I probably wouldn't have used it. Oh, how could I forget? There's also the fundamental reason that led us to LibrePCB in the first place. See, there's lots of different design software out there, but one of the things that I was going through at home was a transition of operating system. See, up until now, we've been running everything on Windows, and DesignSpark runs great on Windows. I wanted to increase my Linux skills, so we wanted to get everything set up on an Ubuntu operating system. And I discovered that DesignSpark only runs on Windows. I know, there are probably ways I can get it to run on an Ubuntu setup, but I didn't want to go down that path. I wanted it to run natively on the operating system. LibrePCB is truly cross-platform. It will run on Windows, also run on Ubuntu. I guess it would run on Mac as well. I don't know, I'm not a Mac guy, I couldn't tell you. But that's definitely a plus for LibrePCB. The manufacturing process for both of these pieces of software is, as you'd expect, fairly similar. Here's the output or the settings to generate the output Gerber files in DesignSpark. And in LibrePCB, it's similar. We set up an output job and we can create one for, there's the Gerber files right there, and click go. Once the manufacturing files are generated, I put them up into a zip file and send them off to my favorite manufacturer, which brings us to the sponsored part of this video. I want to send a huge thank you for PCBWay for sponsoring this video. They have been my PCB manufacturer since the beginning. I've been using them for years, and I use them for this run of manufacturing as well. I found PCBWay a long time ago, and they have been excellent to me over the years. If you go to the website PCBWay.com, you'll see how easy it is to manufacture your custom printed circuit boards. There's an instant quote section on the website where you can fill in a bunch of information on the design. Let's try a 100mm by 100mm board. I'll ask for 10 pieces. You can see the rest I'll leave at default. Here's 2 layers. We have an FR4 standard material. TG150, it actually says here that they've upgraded this and they'll automatically put you to S1000H at no extra charge. Thickness is 1.6. We'll leave that alone. Min track spacing at 6 mil. Min hole size is 0.3 milliliters. I don't like green. Let's go with blue. White silkscreen is fantastic. The rest of it will leave default, and 1 ounce of copper will be placed on our traces. Do that. Click calculate. Look at this. That's amazing. $5. How can you beat that? The bulk of the cost here is the shipping, but that's because I'm Canadian. But it's not even that expensive. $20 to ship halfway around the world in 3 days' time? I clicked go, and 3 days later, they sent me this. Before I show you the manufactured board, let's take a look at some of the design changes that we've implemented. Here's the original driver board. You can see the 2-pin connection that leads to the LED output over here. Beyond a layout change, the biggest difference you'll notice is these 3 screw terminals. 2 for the LED outputs, 1 over here, and 1 for a thermal connection, which will also provide stability for that board. Here's the original controller board with the 4 anchors that turned out to be irrelevant. And you can see the driver connections right over here. There's one of them, and here's the other. Power connection is up on the top over here. The updated controller board is the exact same size as the original, but with some creative layout adjustments, we've been able to fit 6 drivers onto the same size board. Each driver has its own screw terminal which serves as the thermal connection, and you can also see 2 more screw terminals here which serve as the power. The updated controller board still has the option for the rotary connection or the switches you can see over here, and we also found room for a power LED. We also upgraded the luminaire, which is going to be printed on an aluminum PCB. It still has room for 3 LEDs, but it grew a little in size. The inner holes will be used to anchor it to an enclosure, while the outer holes will be used as screw terminals to feed it the power. One, of course, is going to be the anode, and the other is going to be the cathode. And we had to do the surface mount style too, so here's the driver using the surface mount components, and here's a surface mount version of the controller. Look at how beautiful these boards are. Here's the through-hole design for our revised controller. Here's the same controller circuit, this time in surface mount style. Beautiful. Here's the drivers. These are the through-hole version. I asked PCBWay to create these in a panel for me. That way I actually get 6 of them on one board, and they're super easy to take apart. And here's the SMD version. I also had them create the aluminum LED modules as well. Aluminum backed. Let's put it together. Okay, so after putting all those boards together, it didn't work. Oh my gosh, I started worrying. There was something wrong with the manufacturing. Did I burn apart? What happened? I spent days debugging it to try to figure out where the problem was. A part of me was even thinking maybe there was a manufacturing error. I have been with PCBWay for so long, they could not have done something wrong, but maybe, just maybe they did. And then I found out where the problem was. Here is a schematic for the bit counters in the old design. Now, if you remember, the purpose of the counters is to count from 0 to 16, signifying the various levels of intensity. And the counters basically allow you to go through those levels and not exceed 16, and when you go down to not exceed 0. That's what this circuit is designed to do. Notice the actual counter chips here. These are the 4516 binary counters. This is the lowest significant byte, and here is the most significant byte. Each one of these chips is a 4-bit counter. So to count from 0 to 16, you only need 1, but our design allows us to count from 0 to 32 or even 0 to 64, which is why there's space for 2 of these chips. These particular chips have a preset function which allow us to preset the count at these chips on startup. And it's done by using these 4 pins, P1, P2, P3, and P4. Now, we're not using the preset function for this particular circuit, so all of these presets are connected to ground. Notice the blue line over here. The preset enable is also ground. That tells the chip to not use the preset. You see where I'm going with this? Here's the equivalent upgraded circuit in LibrePCB. These are my 2 4516 counters, the lowest significant byte and the most significant byte. Here are the preset values, P1 through P4. They're all tied together, all chips, and they're down to ground, as you can see over here. The problem, though, was the preset enable. I tied this to plus 12 volts. Right away, I'm going to give another point to DesignSpark because you see all of my lines here are green. And in DesignSpark, I've color-coded them. Here's my light blue for ground and my orange-red for power. I have nobody to blame but myself. This was clearly user error. The manufacturer had nothing to do with this. In fact, PCBWay did what they did so well. They followed my design exactly as I instructed, and they built exactly what I asked for. Of course, I asked for the wrong thing. Now, in some incredible spark of luck, the 4516 counter IC that I'm using positions the preset pin right on pin 1. That's an awfully convenient place to put a pin. So I went and made an adjustment. These 2 ICs here, these are the 4516 counter pins. And basically, with pliers, very gingerly disconnected the first pin and wired it to ground. And I did the same on this side. After doing that, it worked. Here's the SMD version of that same controller, and here's the 4516 counter chip here. And you can see my wire connection, which leads to ground. Different position on this one. I didn't actually wire it up to the ground pin. Nonetheless, it is still grounded. Here's the SMD driver. And off on the side here is our LED wired up with those beautiful screw terminal attachments, which I absolutely love. Here's the screw terminal attachments for the driver and the power screw terminal attachments working wonderfully. Flipping this over. Watch it work. Beautiful. Oh, I am so happy that that worked. I was getting such a headache trying to trace that down. Hey, in the end, I figured out it was my fault, and at least now I know where the problem is. And once I solved that problem, it worked like a charm. So now I got to figure out what to do next. I may have to reach out to PCBWay and manufacture a fixed board. But no, that's a problem for another day. For now, I think I'm done.